These are the 24 human beings who have ever left the protection of Earth's magnetic field, and every single one of them was gone for less than 2 weeks. This is the story of what happens to a human body and a human mind the farther they travel from home, and everything in it comes from what's actually been measured, recorded, and confirmed by the people who study spaceflight for a living. If you want more science explained in plain language, go ahead and hit subscribe, and let's get into it. Space doesn't get scarier because of anything hiding out there in the dark. It gets scarier because of what distance itself does to a person, and that's a much harder thing to shake off than a monster would be. The radiation gets heavier the farther out you go. The silence between you and Earth gets longer. The body starts failing in small, measurable ways, and the mind starts failing in its own quieter way right alongside it. None of this needs a creature behind it. It only needs enough distance and enough time, and this year, for the first time in more than 50 years, humans pushed that distance further than anyone alive had ever gone. So let's start with the shield most people never even think about, because everything else in this story only makes sense once you understand what it is you're leaving behind. The shield we didn't know we had. Every person who has ever lived, worked, or died on this planet has spent their entire life inside a bubble without ever noticing it was there. It's called the magnetosphere, and it comes from the churning metal core sitting thousands of miles beneath our feet. That magnetic field wraps around the whole Earth and deflects the worst of what the universe throws at us: streams of charged particles boiling off the sun, and a steadier, quieter bombardment arriving from deep space beyond it. You can't feel it, you can't see it, and most people go their entire lives without once knowing it's there. But it's doing an enormous amount of work every second, and the instant you leave it, that work simply stops. Here's the number that puts the whole thing in perspective. In the entire history of human spaceflight, only 24 people have ever traveled beyond Earth's magnetosphere, and every one of them was an Apollo astronaut. Their time spent beyond that shield maxed out at around 12 days, the length of the Apollo 17 mission, and that's the complete sum of human experience living outside our planet's protective bubble. Everyone else who has ever gone to space, including every single crew member who has ever lived aboard the International Space Station, has stayed inside low Earth orbit, still safely tucked under that same magnetic field. 12 days is barely a long weekend, and a mission to Mars is currently projected to take 2.5 to 3 years. The gap between what scientists actually know and what humanity is about to attempt isn't small. It's almost the entire length of the mission itself, and that gap is where this story really starts. The radiation no wall can stop. Once a spacecraft passes beyond the magnetosphere, 2 different threats start hitting it at once. The first is a solar particle event, a burst of high-energy protons thrown out during a solar flare, and while these bursts are genuinely dangerous, they're at least tied to the sun's activity in ways scientists can track, and shielding can block a meaningful portion of them. The second threat is the one that should actually worry you, because there's currently no good way to stop it at all. It's called galactic cosmic radiation, and unlike solar particles, it doesn't come from our sun, it comes from somewhere else in the galaxy entirely, likely flung outward by exploding stars long before humans existed to notice. These particles are heavy, fast-moving, and highly charged, and they hit with enough force to pass straight through the kind of shielding that would easily stop a solar flare. You can't build your way out of this problem with thicker walls, because thicker walls simply don't stop it. So what does that radiation actually do to a person exposed to it? Several Apollo astronauts reported seeing flashes of light behind their closed eyelids during their missions, and scientists believe those flashes came from high-energy particles tearing straight through the retina in real time, while the astronauts' eyes were shut and their brain was simply along for the ride. Picture that for a second, lying in the dark of a spacecraft, and watching your own eyes register hits from particles that have been traveling since long before recorded history began. That same exposure is considered the likely explanation for why Apollo astronauts developed cataracts at unusually high rates later in their lives, and some research has even linked their radiation exposure to a heightened risk of cardiovascular disease through damage done to the lining of their blood vessels, though scientists are still working out how strong that connection really is. What isn't up for debate is the underlying mechanism itself. This radiation damages DNA directly, it can trigger cancer, and it weakens the immune system. And unlike nearly every other risk astronauts face, its effects are cumulative. There's no reset button. The longer the mission runs, the worse the exposure gets, and it simply keeps adding up. There's also a slower, quieter form of damage happening underneath all of that. Research into galactic cosmic radiation has found it can produce long-term changes in brain structure, specifically inside the hippocampus, which happens to be the part of your brain most responsible for learning and for forming new memories in the first place. In other words, the exact radiation an astronaut traveling to Mars will be exposed to for years is a type of radiation with a documented relationship to the parts of the brain that quietly make you who you are. And here's the piece that should really sit with you a moment. Every bit of that comes from just 24 people, spread across a combined total of a few hundred days. A round trip to Mars means years of continuous exposure, and scientists genuinely don't know the full extent of what that looks like yet, because nobody in human history has ever done it. Whoever eventually makes that trip will, in a very real sense, become the experiment. The body starts coming apart. Radiation isn't the only thing distance does to a person. The absence of gravity itself begins dismantling the human body, and that process starts almost immediately, long before radiation has time to build up. Bone loss in space was first documented back in the mid-1970s aboard the Skylab space station, when crew members were measured losing between 1 and 2% of their bone mass every single month they stayed in orbit. That's a rate of loss far faster than the gradual bone loss most elderly people experience from ordinary age-related osteoporosis here on Earth. And after 6 months in space, an astronaut's bone scans can start to resemble the bones of an elderly woman living with osteoporosis. In the weight-bearing bones specifically, the ones running through the legs, hips, and spine, astronauts have lost as much as 20% of their bone mass over just a 6-month stretch. A large analysis pooling data from nearly 150 astronauts found the damage isn't spread evenly across the skeleton at all. The skull, strangely enough, actually gained a small amount of density, but the lumbar spine and pelvis lost more than 6%, and the lower limbs lost more than 5% overall, continuing to shed roughly 0.8% every single month a crew member stayed in space. Muscle fares just as badly, if not worse. Short missions alone have produced muscle loss somewhere between 10 and 20%, and without any countermeasures at all, that number could climb as high as 50% on a genuinely long-duration mission. That's not some minor inconvenience you shrug off. That's the difference between an astronaut walking off a spacecraft under their own power and one who has to be carried out on a stretcher. Then there's what happens to your eyes, and this one might be the strangest of them all. It's called Spaceflight-Associated Neuroocular Syndrome, or SANS for short, and it wasn't even formally identified as a medical condition until 2011, which tells you how recently we've started to understand it. In one study of NASA astronauts who had completed long-duration spaceflight, 81% of them showed at least one measurable eye finding tied to SANS, and other research puts the rate closer to 70% among long-duration crew members specifically, with 15 to 20% developing a version severe enough to be considered clinically concerning. The leading theory behind it is almost eerie in how simple it sounds. On Earth, gravity constantly pulls fluid in your body downward toward your feet, all day, every day, without you ever thinking about it. In microgravity, that pull vanishes entirely, and fluid drifts upward instead, toward the head and face, which is why astronauts' faces look visibly puffy once they reach orbit. But that fluid shift doesn't stop at puffiness. It's believed to raise pressure inside the skull, physically flatten the shape of the eyeball, and cause swelling around the optic nerve itself. Astronauts have returned to Earth with globe flattening, folds in the tissue at the back of the eye, and a permanent shift in how their eyes focus, changes that in some cases have lasted for years after landing. So far, no astronaut has lost their vision entirely because of it, but no human being has stayed in microgravity long enough yet for anyone to know where that ceiling actually sits. The enemy already inside you. Here's something most people have genuinely never heard before, and it might be one of the strangest findings to come out of spaceflight medicine. Going to space can wake up viruses that have been sitting dormant inside your own body for years, sometimes for decades. Most adults already carry at least one type of herpes virus in a dormant, inactive state, and that family includes the virus behind cold sores, the one behind chickenpox and shingles, and Epstein-Barr virus, which more than 90% of adults carry without ever realizing it. Normally, your immune system keeps these viruses locked down and completely silent. But researchers analyzing astronaut samples found that the stress of spaceflight, the confinement, the disrupted sleep, the radiation, and the surge in stress hormones like cortisol all combine to suppress the very immune cells whose job is keeping those viruses asleep in the first place. The numbers on this are strikingly specific. Among the astronauts studied, the rate of one herpes virus being shed in bodily fluids climbed from 41% on space shuttle missions to 65% during longer ISS stays. Epstein-Barr shedding rose from 82% all the way to 96%, and cytomegalovirus climbed from 47% to 61%. Roughly half of all astronauts studied ended up reactivating and shedding at least one of the 9 known human herpes viruses during or after their time in space. Only a small handful actually developed symptoms, and those were minor, but researchers have been clear that reactivation rates climb the longer a mission runs, which means a 3-year mission to Mars isn't just a scaled-up version of a 6-month ISS stay, it's an entirely different category of biological risk. Your own body, something that's been with you your entire life, quietly becomes less trustworthy the farther out you push it. The body that comes back different. There's one experiment that hands us a rare, almost unfair advantage in understanding all of this, because it controlled for something scientists almost never get to control for: genetics itself. Back in 2015, astronaut Scott Kelly spent nearly a full year, 340 days, aboard the International Space Station, while his identical twin brother Mark, also a retired astronaut, stayed behind on Earth. NASA seized the opportunity to compare the two men directly, tracking blood, stool, and urine samples from both brothers before, during, and after the mission. And because the two share identical DNA, any differences that showed up between them could be attributed far more confidently to spaceflight itself, rather than to ordinary human variation. What turned up was strange enough that the research team initially assumed they'd made a mistake somewhere along the way. Scott's telomeres, the protective caps sitting on the ends of his chromosomes that normally shorten with age and with stress, actually grew longer during his time in orbit. The finding was so unexpected that scientists reran the tests entirely, certain they'd find contamination or some kind of error. The lengthening held up anyway. Then, within 48 hours of landing back on Earth, those same telomeres collapsed, not just back down to where they'd started, but below his pre-flight baseline, alongside a measurable increase in chromosomal damage. Roughly 7% of Scott's gene expression still hadn't returned to normal a full 6 months after he landed. Researchers also documented something called chromosomal inversions and transpositions, essentially gene sequences that had been physically rearranged, changes tied specifically to space radiation exposure, and some of those inversions were still elevated 9 months after he came home. His cognitive performance ran measurably slower for a stretch afterward too. NASA has been careful to point out that his underlying DNA wasn't rewritten, and that most changes did eventually settle back near baseline. But the honest version of this story is that spaceflight left marks on Scott Kelly at the genetic level that outlasted the mission itself by months, in some cases nearly a year. And that was 340 days. A mission to Mars gets measured in years, not months. What spacewalks do to your hands? Even the equipment designed specifically to keep an astronaut alive outside a spacecraft carries its own quiet, well-documented cost, and it lands, of all places, on the hands. Every spacesuit glove used for a spacewalk has to hold pressure against the total vacuum of space, and once pressurized, that glove stiffens into something closer to a rigid balloon than a piece of clothing. Current spacesuits pressurize to about 1/3 of an atmosphere, just enough to keep an astronaut alive, but more than enough to make simple hand motions, gripping a tool, turning a bolt, genuinely difficult and often painful. Spacewalks can run as long as 8 to 9 hours at a stretch, and for that entire time, An astronaut's fingertips are pressed repeatedly against rigid internal structures inside the glove's fingertips, sometimes called thimbles, engineered to give the glove its shape. Researchers analyzing NASA injury records found that close to half of all reported spacewalk training injuries were hand-related, and the most severe outcome of that repeated pressure is a condition called fingernail delamination, in which an astronaut's fingernail detaches completely from the nail bed underneath it. A study examining data from 232 crew members found that roughly 10% had experienced this kind of fingernail trauma, and researchers discovered something unexpected when they went looking for a cause. It wasn't astronauts with long fingers who were most at risk, as engineers had originally assumed. It was astronauts with wider hands, with male crew members whose hand circumference exceeded 9 inches, facing close to a 20% chance of fingernail injury, nearly 4 times higher than crew members with smaller hands. The condition doesn't typically end an astronaut's career, and nails do eventually grow back, but in the moment, it's a serious operational hazard. A nail that detaches mid-spacewalk can snag inside the glove itself, and researchers noted that moisture trapped against the exposed raw nail bed underneath creates a real risk of bacterial or fungal infection, hundreds of miles from the nearest hospital. MIT astronautics professor Dava Newman, who spent 2 decades studying the problem, described some astronauts' response to it plainly. She said she'd heard of a couple of people who had removed their own fingernails ahead of a spacewalk, entirely as a precaution, rather than risk losing them mid-task while working outside a spacecraft with nothing between them and open space but a suit already causing the injury in the first place. The invisible collisions. There's one more threat worth naming, and it doesn't come from inside the human body at all, which makes it easy to forget about, mostly because, most of the time, absolutely nothing happens. But space isn't empty. It's full of micrometeoroids, natural particles left over from comets and asteroids, and orbital debris, fragments of old satellites and spent rocket stages, and both are moving at speeds that make the word small almost meaningless. Orbital debris typically strikes a spacecraft in low Earth orbit, somewhere between 9 and 10 kilometers per second. Micrometeoroids hit even faster, often around 20 kilometers per second, which works out to roughly 60 times the speed of sound. At those velocities, even a particle smaller than a grain of sand carries enough energy to chip a window, punch through a solar panel, or in a worst-case scenario, breach the hull of a spacecraft with people inside it. For a vehicle the size of the International Space Station, a debris strike has historically ranked as the single greatest risk to the entire mission, greater than launch, greater than re-entry. Most of these impacts are small enough that the crew never even notices them, quietly absorbed by layered shielding built for exactly this purpose. But not always. In one documented case, a micrometeoroid struck one of the ISS cupola windows directly, and the crew immediately closed its protective shutter while engineers assessed the damage from the ground. It's the kind of event that unfolds quietly, almost administratively. A chipped window, a shutter closed, an inspection scheduled, and it's also a reminder that everything standing between a human being and space, from the walls of the spacecraft to the glass they're looking out of, is holding back an environment that is, by any honest measure, actively hostile. Beyond Earth orbit, on a years-long transit to Mars, there's no ground-based radar tracking the debris field the way there is closer to home. A crew heading outward is simply trusting the odds, and the odds say most of the time they'll be fine. The sound of air leaving everything covered so far unfolds slowly, over weeks and months. But distance also raises the odds of something that happens in seconds, and there's already a real, documented case of exactly that. On June 25, 1997, cosmonaut Vasily Tsibliev was manually guiding an unmanned Progress resupply ship toward Russia's Mir space station, using a video feed to judge its speed and distance, a setup that turned out to be dangerously unreliable. The image on the screen barely changed size as the vehicle closed in, which meant Tsibliev couldn't tell how fast it was actually moving until it was already too late to stop it. Fellow cosmonaut Alexander Lazutkin spotted the incoming spacecraft and later described it as looking full of menace, like a shark. Moments later, the 7,200-kilogram Progress vehicle slammed into a solar array, then plowed directly into Mir's Spectre module, punching a hole clean through the hull. American astronaut Michael Foale, who was aboard Mir at the time, described what happened next to the BBC. "It was frightening for 1 or 2 seconds," he said, and his first thought was whether they were about to die instantly as the air came rushing out. His calculation, in that moment, was that they had roughly 23 minutes before the crew would start losing consciousness if nothing were done. Lazutkin was the one who told Foale to get into the escape ship, but Foale left it once he realized his crewmates weren't following him. They were staying behind to try to save the station instead. Working together, Lazutkin and Foale managed to sever the cables connecting Spectre to the rest of Mir and sealed off the breached module entirely, cutting off the leak before it could depressurize the whole station. It worked. But the impact had also knocked Mir into an uncontrolled spin, tumbling roughly once every 6 minutes, and the same collision that punctured the hull had also killed the power to the gyrodynes needed to stabilize it. The crew eventually brought the station back under control, and weeks later, 2 cosmonauts carried out an internal spacewalk, wearing full suits inside the depressurized airless module, just to reconnect power cables and recover about 70% of Mir's electricity. The hole in Spectre's hull itself was never repaired. It's considered, to this day, one of the most serious collisions in the history of human spaceflight, and it happened in low Earth orbit, close enough to home that rescue and support were still, in theory, an option. A mission to Mars won't have that option. A depressurization event years from Earth, with no nearby station to retreat to, and no rescue vehicle within even a year of arriving, would have to be handled entirely by the people already on board, with whatever tools and training they'd brought with them. The food that stops working. There's an even more mundane problem waiting at the far end of a long mission, and it's one most people would never think to worry about. The food itself starts to fail. Researchers who study space nutrition have found that certain vitamins degrade steadily during long-term storage, with riboflavin, vitamin A, and vitamin C breaking down the fastest, worn away by exposure to heat, radiation, and oxygen over time. Shelf life studies on current space food systems have found that most products remain safely edible for up to about 2.5 years, which sounds like a long time until you remember that a full round-trip mission to Mars, including surface time, is expected to run 2.5 to 3 years, right at or beyond the edge of what today's food supply can reliably provide. Nutritionally, the numbers get more specific the closer you look. One study following 11 astronauts through long-duration missions on the International Space Station found crew members were consuming, on average, only about 80% of their recommended energy intake, and by landing day, their body weight had measurably dropped. Blood tests after their missions showed changes in iron levels and blood chemistry connected to that reduced intake. On top of the nutrition problem, taste itself changes in space, tied to the same fluid shift that affects the eyes, and astronauts have described a kind of persistent nasal congestion in orbit that dulls their sense of taste, leading many of them to reach for stronger flavors and heavier spices just to make food taste like anything at all. None of this is life-threatening on a 6-month ISS rotation, where supply ships arrive regularly and a diminished appetite is an inconvenience rather than a crisis. On a mission where the food has to last the entire trip, packed before launch and never resupplied, slowly losing its nutritional value while the person eating it is already fighting bone loss, muscle loss, and a suppressed immune system, it becomes one more small, compounding problem stacked on top of everything else already working against the body. The hack that kept 3 men breathing return, for a moment, to Apollo 13, because the danger that nearly killed its crew wasn't the explosion itself. It was what happened to the air inside the spacecraft in the days that followed. After the oxygen tank explosion crippled the command module, Jim Lovell, Jack Swigert, and Fred Hayes crowded into the lunar module, a compact vehicle originally built to sustain 2 astronauts for roughly 2 days on the surface of the Moon, not 3 astronauts for the 4 days it would now take to limp back to Earth. The module's round lithium hydroxide canisters, the chemical filters responsible for scrubbing carbon dioxide out of the air the crew was breathing, were built for exactly that smaller workload, and with an extra person on board exhaling into the same enclosed space, Those canisters started running out far faster than anyone had planned for. Left unaddressed, the carbon dioxide building up in that small cabin would have risen to poisonous levels well before the crew ever made it home. There was a solution, technically. The command module, sitting powered down and unused just a few feet away, had plenty of spare lithium hydroxide canisters left. There was just one problem. They were square, built for a completely different filtration system, and the sockets waiting to receive them in the lunar module were round. Square peg, round hole, in the most literal and life-threatening sense imaginable. Engineers back in Houston went to work building a fix, using nothing but items the astronauts already had on board. A plastic bag from a used spacesuit's liquid cooling garment, cardboard torn from the cover of a flight manual, a length of hose, and duct tape. Lots of duct tape. The instructions transmitted up to the crew ran to nearly 20 separate steps, from pulling a bag down over the square canister and sealing it with tape, to routing a hose from that improvised seal into the ship's air cleaning system, to watching a meter for the carbon dioxide level to finally begin dropping towards something survivable. NASA later nicknamed the finished device simply the mailbox. The crew followed the taped-together instructions exactly, wired the whole assembly together by hand, floating in a freezing, powered-down spacecraft, with their lives depending on cardboard and duct tape, performing exactly as engineers on the ground, working from photographs and spare parts in a simulator, had calculated it would. It worked. The carbon dioxide levels fell back to a safe range, and 3 men, who very nearly suffocated on their own, exhaled breath, made it home instead. It remains one of the clearest examples in the history of spaceflight of just how quickly the ordinary business of simply breathing can turn into the single most dangerous problem on a mission, and how far from home a crew has to be before an engineering team's only tools are the leftover contents of a spacecraft's junk drawer, the bacteria that travel with you. There's a version of every astronaut that never gets talked about much, the trillions of bacteria living inside their gut, and it turns out that community changes too, in a remarkably consistent way, every single time. Researchers developed an analytical tool specifically to compare gut microbiome data across multiple spaceflight experiments, spanning mice flown on the space shuttle, mice flown to the International Space Station, and human data pulled directly from the twins study involving Scott and Mark Kelly, and found something striking. Spaceflight produces a specific, repeatable shift in the ratios, abundance, and diversity of gut bacteria, and that shift looks essentially the same whether it's happening in a mouse or in an astronaut who just spent nearly a year in orbit. Scott Kelly's own gut microbiome data lined up with the same pattern researchers had already identified in animal studies, the same major bacterial groups shifting in the same direction, alongside a modest increase in overall bacterial diversity. What makes this particularly strange is what it isn't caused by. Researchers directly compared the microbiome changes seen in spaceflight against microbiome changes recorded in separate, Earth-based studies specifically measuring the effects of radiation on the gut, and the two didn't match. Radiation clearly does affect gut bacteria on its own, but the pattern doesn't resemble what happens in orbit, which means the shift is being driven by something else entirely tied to the spaceflight environment itself. Likely some combination of microgravity, stress, and the same disrupted sleep and confinement already stacking up everywhere else in the body. The gut microbiome isn't a side character in human health. It's deeply tied to digestion, to metabolism, and increasingly researchers believe, to immune function and even mood. Separate studies have found specific, measurable changes after spaceflight, increases in certain bacterial groups capable of turning opportunistic under stress, alongside decreases in other bacterial populations known for anti-inflammatory effects. One researcher leading this work described the pattern in gut bacteria seen during spaceflight as looking, more than anything else, like stress, the same kind of signature you'd expect to find in the gut of someone enduring a prolonged, unrelenting, difficult period. Because in a very real, measurable sense, that's exactly what a body in space is going through, one system at a time, for as long as the mission lasts. The heart that forgets its shape. There's one organ in particular that changes shape almost immediately in orbit, and it happens to be the one keeping every other system in the body alive. Echocardiogram studies comparing astronauts' hearts before and during spaceflight found something genuinely strange. the heart itself becomes measurably more spherical in microgravity. Researchers measure this using something called a sphericity index, and across a study of a dozen astronauts, that index dropped from an average of just over 2 before flight down to around 1.82 once they'd spent time in orbit. A real, physical shift toward a rounder, more globular shape. The explanation traces back to the same fluid shift responsible for puffy faces and eye damage. On Earth, the heart works constantly against gravity to push blood upward through the body. In microgravity, with that resistance gone, the heart doesn't have to work nearly as hard, and its muscle mass starts to shrink almost immediately, within days, in direct response to the lighter workload. That sounds almost like a break, a rest, for an organ that spends a lifetime fighting gravity. It isn't. When astronauts eventually return to Earth, that same weakened, atrophied heart suddenly has to relearn how to fight gravity again, all at once, and many astronauts become lightheaded or briefly pass out upon standing, a condition called orthostatic hypotension, caused by blood pressure dropping too fast because the heart and blood vessels have partly forgotten how to respond to being upright. Researchers have also documented arrhythmias, irregular heartbeats, occurring during spaceflight itself, and there's ongoing concern that radiation exposure in space may accelerate the hardening and narrowing of arteries over time. The real worry sits with missions that last far longer than a typical ISS rotation. One analysis modeling what happens to the cardiovascular system on a Mars-length mission found that re-exposure to Earth's gravity after more than 3 years in microgravity is expected to produce extremely high rates of orthostatic intolerance, driven by both nerve dysfunction and significant, measurable shrinkage of the heart muscle itself. In other words, the longer the trip out, the harder the trip back, and the heart that carried someone to Mars may not be fully prepared to carry them back off the spacecraft once they've landed. The stones forming inside, you remember, the bone loss covered earlier, the 1 to 2% of bone mass astronauts shed every month in orbit. That calcium doesn't just disappear once it leaves the skeleton. It has to go somewhere, and where it goes creates an entirely separate problem. As bone breaks down in microgravity, the calcium it releases enters the bloodstream and eventually gets filtered through the kidneys, raising the level of calcium present in an astronaut's urine. Combine that with something else spaceflight does, reduce the amount of fluid an astronaut is actually drinking and processing, and you get exactly the conditions kidney stones need to form. Researchers studying astronauts on 4 to 6 month ISS missions found that regardless of which exercise countermeasure a crew member used, their risk of forming a renal stone increased during spaceflight, and identified low urine volume as a key factor driving that risk upward. This isn't a hypothetical either. At least 14 American astronauts have developed kidney stones within a documented 5-year stretch, and separate research counts 12 NASA astronauts who developed the condition after their missions specifically, along with at least one cosmonaut who developed a stone during an actual mission while still in space. Kidney stones are miserable on Earth, where a hospital and pain medication are usually close by. In the middle of a years-long transit to Mars, with no ability to turn around and no real-time guidance from Earth beyond a message that might take 20 minutes each way to arrive, a kidney stone stops being an inconvenient trip to the emergency room and becomes a medical crisis the crew has to manage entirely on their own. The sickness that comes first before any of the long-term damage has time to build up, before the bones start thinning or the eyes start changing shape. There's something waiting for nearly every astronaut in the very first hours of a mission, and it has nothing to do with toughness or training. NASA's own medical documentation states that space adaptation sickness affects somewhere between 70 and 90% of crew members, and space motion sickness specifically, the nausea and vomiting version of it, hits around 73% of astronauts during the first days of an initial flight. It doesn't discriminate by experience or physical fitness. Some of the most seasoned fighter pilots NASA has ever selected, people who spent careers pulling high-speed maneuvers without a flicker of discomfort, have arrived in orbit and immediately felt sick, while other astronauts with a documented history of motion sickness on Earth sailed through their first days in space without a single symptom. NASA has been direct about this in its own literature, saying that ordinary motion sickness history simply isn't a reliable predictor of who will suffer in orbit and who won't. The cause traces back, once again, to that same fluid shift responsible for puffy faces and swollen optic nerves. Without gravity pulling fluid downward, the inner ear's balance system and the eyes suddenly start sending the brain two different conflicting stories about which way is up, and the disorientation that results can trigger nausea, vomiting, facial swelling, and nasal congestion, all cresting hardest in that first week before the body starts to adjust. Separately, more than half of astronauts, according to NASA's own figures, around 52%, experience a specific kind of back pain in their first 2 to 5 days in orbit, caused by the spine straightening out once the usual compressive weight of gravity disappears from it entirely. There's a practical, deadly serious reason NASA takes all of this seriously enough to document it in official technical briefs. Spacewalks are never scheduled during those first few days for exactly this reason, because vomiting inside a sealed spacesuit can be lethal, capable of obscuring an astronaut's vision or blocking their airflow entirely, with no way to remove the helmet in the vacuum of space to fix it. Most crew members do adapt within roughly 3 days, as the brain slowly recalibrates itself to a world with no clear up or down. But for missions to the Moon or Mars, that adaptation period has to happen before a single productive hour of work can even begin. An entirely predictable multi-day stretch of sickness built into the very start of the very trip. Counting the radiation in numbers. Earlier, this described the danger of galactic cosmic radiation in general terms: unstoppable, cumulative, damaging. Here's what it actually adds up to, in the specific units scientists use to measure it. On Mars's surface, data collected by NASA's Curiosity rover puts the average radiation dose rate at about 0.67 millisieverts per day. For comparison, a single chest X-ray on Earth delivers roughly 0.1 millisieverts. That means simply standing on the surface of Mars exposes a person to something in the range of multiple chest X-rays worth of radiation every single week, not from a hospital machine, but from the environment itself, all day, every day, indefinitely, because Mars lost its global magnetic field billions of years ago and has never had a shield like Earth's to offer any protection. The transit itself is worse than the surface. One detailed estimate calculated that the radiation exposure across a roughly 500-day round trip to Mars, mostly absorbed during the unshielded months spent traveling through interplanetary space rather than the time spent on the Martian surface itself, adds up to approximately 930 millisieverts, a number that significantly exceeds both annual safety limits and, in some cases, an astronaut's entire allowed career radiation limit, all from one single mission. Radiation exposure is measured against real, tracked health outcomes, using something called risk of exposure-induced death. And the European Space Agency has stated plainly that a mission to Mars could expose an astronaut to radiation doses up to 700 times higher than what a person receives on Earth. NASA's own safety standard limits astronaut radiation exposure to a 3% increased lifetime risk of fatal cancer. Analysis modeling the risk of an actual Mars mission found that central estimates for radiation-induced death and serious illness could exceed 5% and 10% respectively, with the upper bound of that uncertainty range climbing as high as 10% and 20%. A separate, more recent risk model calculated the added lifetime cancer risk, specifically from a Mars mission, at somewhere between 2.5% and just under 4%, depending on the astronaut's sex, on top of whatever cancer risk that person already carried simply from being alive. None of these numbers are secret or hidden. They're published, tracked, and factored directly into how space agencies decide who is allowed to fly and for how long. They are also, by every agency's own admission, dangerously close to limits nobody fully knows how to guarantee compliance with, on a mission that hasn't happened yet. The sleep that never comes. Add one more weight to everything already stacked against the human body out there. Astronauts in space are, almost without exception, running on a persistent sleep deficit, and researchers have been documenting it for as long as they've been tracking it. NASA schedules 8.5 hours of sleep per night for crew members. In the largest study ever conducted on the subject, tracking more than 8,000 nights of sleep combined, both on Earth and in orbit, across dozens of astronauts, the actual average came out closer to 6 hours a night. In some analyses, closer to 5 hours and 58 minutes. And that shortfall isn't some temporary adjustment period either. Astronauts were already averaging only about 6.5 hours of sleep a night for the full 3 months leading up to launch, before they'd even left the ground. The reasons pile up fast once you're actually in orbit. Aboard the International Space Station, crew members experience a sunrise or sunset roughly every 45 minutes, which adds up to as many as 16 full day-night cycles inside a single 24-hour period, more than enough to scramble the body's circadian rhythm, even with careful lighting controls in place. Add in the noise, the cramped sleeping quarters, altered air pressure, the psychological weight of isolation and confinement, and irregular mission schedules that sometimes demand what researchers call slam shifts, abrupt changes to a crew member's entire sleep-wake cycle, and consistent, restful sleep becomes something close to structurally impossible. The response, for most of spaceflight history, has simply been medication. Researchers found that more than 70% of astronauts used sleep-promoting drugs like Zolpidem, sold on Earth under the name Ambien, at some point during their missions, and on space shuttle missions specifically, crews took them on more than half of all nights spent in space. Some crew members have even been documented taking a second dose mid-sleep, entirely on their own judgment, suggesting the first dose simply hadn't worked, all while operating a spacecraft that other people were depending on them to run alertly. None of it gets easier the farther out you travel either. Once a mission leaves Earth orbit entirely, that rapid sunrise-sunset cycle disappears, but a new problem takes its place. On the way to Mars, researchers point out that crews will eventually need to synchronize themselves to a Martian day, which runs 24 hours and 39 minutes, just slightly longer than Earth's. A tiny mismatch that compounds, minute by minute, into a slowly drifting body clock over the course of a years-long mission. Chronic sleep deprivation on Earth is already linked to metabolic disorders, cardiovascular disease, and impaired decision-making. And in space, that same deprivation gets layered directly on top of radiation exposure, bone loss, isolation, and a body that's already struggling to keep up with everything else being asked of it. The mind alone. None of that touches what happens inside a person's head, and that might genuinely be the part with the least room for error, because unlike bone density, nobody can put a number on a person's breaking point ahead of time. The largest simulation of long-term isolation ever attempted was called Mars 500, run between 2010 and 2011 by the Russian Academy of Sciences, alongside international partners. 6 men, 3 Russian, 2 European, 1 Chinese, sealed themselves inside a mock spacecraft for 520 days, matching the length of an actual round trip to Mars, with no way out and no real contact with the outside world beyond simulated, deliberately delayed communication. Researchers who studied that crew afterward found real, measurable psychological strain running through the group. One crew member experienced mild to moderate depression for most of the confinement. 2 others developed abnormal sleep-wake cycles that never fully settled. Another reported insomnia, paired with genuine physical exhaustion. And remember, this was only a simulation. These men knew at every moment that the isolation was voluntary, that the walls around them sat safely on Earth, and that if something went truly wrong, a door could eventually open. A real Mars crew won't have that option waiting in their back pocket. A separate set of experiments called HICs ran in Hawaii, on the slopes of Mauna Loa volcano, where crews of 6 lived inside a small dome for missions lasting 4, 8, and 12 months at a stretch, wearing simulated spacesuits any time they stepped outside its walls. Researchers monitoring these crews found a consistent pattern emerging. Stress hormones spike hard right at the start of isolation. Then dopamine and serotonin levels begin dropping as the deprivation truly sets in, followed by real disruptions to how well the team functions together. And finally, a stretch of instability that tends to get worse right around the halfway point of a mission, not near the end like you might expect. For an 8 to 12-month mission, that danger zone tends to land around the 6-month mark, and for a real Mars mission running 2.5 to 3 years, that would put the most psychologically dangerous stretch somewhere in the middle of a journey most people can't fully picture living through. A full mission to Mars, counting transit in both directions plus time spent on the surface, currently averages 2.5 to 3 years, and researchers studying the psychological toll list, anxiety, depression, digestive problems, loneliness, and even blood pressure changes among the documented risks of isolation and confinement at that scale. None of this is speculation. It's already been measured in the people who volunteered to simulate it, and it's still just a simulation. The growing silence. Even if the body somehow holds and the mind somehow holds, there's a third factor that shifts the farther you travel, and it might be the most quietly unsettling piece of all: the growing delay before anyone on Earth can even respond to you. On the Moon, the communication lag Apollo astronauts dealt with sat around 1.3 seconds, barely noticeable inside an actual conversation. On Mars, depending on exactly where the two planets sit in their orbits, the one-way delay stretches anywhere from about 3 to 22 minutes. Round trip, a simple exchange like asking how someone's doing and getting an answer back can take as long as 44 minutes from start to finish. There is no version of a live phone call with Earth from Mars. It simply doesn't exist as a possibility. Every exchange becomes something closer to a recorded voice message, sent out into the dark and then waited for. And it gets worse on a fixed schedule. Roughly every 26 months, Mars and Earth line up on exact opposite sides of the Sun, an event called solar conjunction. And during that period, which lasts around 2 weeks, the Sun's own interference blocks communication almost entirely. NASA already deals with this today with its Mars rovers, deliberately halting new commands during that window because a corrupted signal sent to a machine millions of miles away can't be corrected in real time once it's already on its way. For a rover, that means 2 weeks of silence. For a human crew, that means 2 weeks with no meaningful way to call home, no matter what happens on either end. That delay means any Mars-bound crew will need a level of independence no ISS crew has ever needed, because there simply is no real-time help arriving from mission control during an emergency. Every problem that takes more than a few minutes to solve has to be solved by the people standing right there, alone, with nothing but what they brought along with them. The new farthest point. For 56 years, one single number stood as the absolute limit of how far a human being had ever traveled from home: 248,655 miles. That record wasn't set on purpose. It was set entirely by accident, in the middle of a rescue. In April of 1970, Apollo 13 was on its way to land on the Moon when an oxygen tank exploded, crippling the spacecraft and instantly ending any hope of a landing. The only way to bring astronauts Jim Lovell, Jack Swigert, and Fred Haise home safely was to loop the damaged spacecraft around the far side of the Moon and let its gravity slingshot them back toward Earth. And that emergency maneuver, born entirely out of survival, happened to carry the 3 men farther from Earth than any human had ever traveled before. Nobody celebrated in the moment. The astronauts were cold, exhausted, and living inside a powered-down spacecraft with absolutely no guarantee they'd make it back alive. That accidental record stood for 56 years, right up until April 6, 2026, when NASA's Artemis II mission broke it. This time, completely on purpose. Astronauts Reed Wiseman, Victor Glover, and Christina Koch, together with Canadian Space Agency astronaut Jeremy Hansen, surpassed Apollo 13's distance during a planned lunar flyby, ultimately reaching a maximum distance of roughly 252,756 miles from Earth, where the moment carried its own piece of history woven directly into it. Jim Lovell, the commander of Apollo 13, had died in August of 2025, just months before Artemis II ever launched. Before his death, though, he'd recorded a wake-up message for the new crew, and on the very morning they were about to break his 56-year-old record, that message played back for them. "Welcome to my old neighborhood," Lovell said. "It's a historic day, and I know how busy you'll be, but don't forget to enjoy the view." A record set by accident, in the middle of a crisis, handed down by name to the people who finally broke it on purpose, decades later. Distance, it turns out, isn't just a number sitting on a chart somewhere. It's a relationship that gets passed down from one generation of explorers to the next. The edge of everything. If Apollo 13 and Artemis II represent the farthest any human being has ever physically traveled, there's a separate record entirely for the farthest anything human-made has gone, and the scale of that number makes the astronaut distances look almost small by comparison. Voyager 1 launched back in 1977, and according to recent tracking, it now sits about 164 astronomical units from Earth, meaning it's roughly 164 times farther from Earth than Earth itself sits from the Sun. It's currently moving at close to 38,000 miles per hour. Back in 1998, it passed Pioneer 10 to become the most distant human-made object ever built, a title it's held on to ever since. And in 2012, it crossed the heliopause, the outer boundary of our solar system's influence, becoming the first spacecraft in history to enter true interstellar space, the open region that exists between stars. Late in 2026, Voyager 1 is expected to cross a milestone that's genuinely hard to hold in your head. 1 full light day from Earth. That means a radio signal, moving at the fastest speed anything can move anywhere in this universe, will take a complete 24 hours just to reach it. Right now, a message already takes over 23 hours to arrive. Voyager 1 currently sits about 15.7 billion miles away, and it has taken the spacecraft nearly 50 years to travel that distance. Sit with what that actually means for communication. If Mission Control says good morning to Voyager 1, it will be a full day before those words even arrive, and another full day before any reply makes its way back to Earth. 1 sentence and 1 reply takes 2 entire days from start to finish. Voyager 1's transmitter still broadcasts using just 23 watts of power, less than the power drawn by a refrigerator light bulb, and it's still being picked up across billions of miles by NASA's Deep Space Network, a set of antennas positioned around the globe specifically so one of them is always pointed the right direction as the planet turns beneath it. On board, Voyager 1 carries something called the Golden Record, a gold-plated copper disc holding greetings recorded in 55 different languages, selected pieces of music, natural sounds recorded on Earth, and 116 encoded photographs, a kind of message in a bottle meant for anyone, or anything, that might one day find the spacecraft millions of years from now, long after every person who ever built it is gone. Voyager's power source loses about 4 watts of output every single year, and NASA has been switching off its remaining instruments one at a time just to keep the spacecraft transmitting for as long as it possibly can. Eventually, even that 23-watt whisper will fall silent, and Voyager 1 will keep drifting outward anyway, carrying its golden record through the dark, with nobody left listening on the other end. The storm that arrives without warning. Everything covered about galactic cosmic radiation describes a slow, grinding, chronic exposure present every day of a mission, working on the body a little at a time. Solar particle events are a different animal entirely, and they arrive on almost no notice at all. These bursts come from solar flares and coronal mass ejections, violent eruptions on the surface of the Sun that fling protons outward at tremendous speed. Unlike galactic cosmic radiation, which stays roughly constant no matter what day it is, solar particle events are unpredictable, and according to scientists who study the deep space radiation environment, capable of pushing particle radiation to potentially lethal levels within a matter of hours. There's no siren, no visible warning in the sky, nothing an astronaut would necessarily feel until instruments on board start reporting a spike. A crew traveling to Mars, far outside Earth's magnetosphere, with nothing but their own spacecraft between them and the Sun, would need reliable, continuous monitoring simply to know when a lethal event was already underway. The response, if a warning does come through in time, is to shelter. This is the entire reasoning behind proposals for a spacecraft storm shelter, a small, heavily shielded compartment, sometimes built using stored water or blocks of polyethylene, where a crew could retreat and wait out a solar event that might last anywhere from several hours to a few days. It's a reasonable plan, but it depends entirely on early detection, on a crew actually receiving warning fast enough to act, and on a shelter that's been stocked and maintained the entire journey specifically for an event that might never come, right up until the one time it does. The muscles that forget how to fire return to the muscle loss covered earlier, because there's a more specific, more unsettling layer to it that came directly out of the Mars 500 isolation study. Researchers working with the 6 men sealed inside that 520-day simulation didn't just track overall muscle loss, they tracked exactly which kind of muscle fiber was disappearing fastest. The human body relies on two broad types of muscle fiber: slower, endurance-oriented fibers that keep you upright and stable over long periods, concentrated heavily in muscles like the calf, and faster, more powerful fibers, responsible for strength and quick, forceful movement, concentrated in muscles like the quadriceps and hamstrings. Using a specialized device built specifically to measure force output in a confined, Mars mission-like environment, researchers assessed both muscle groups repeatedly across the full 520 days. What they were really testing was whether short bursts of resistance exercise, specifically structured 70-day training blocks, could actually hold that decline back. The underlying finding, echoed across other spaceflight and analog research, is that both the slow postural muscles and the fast, powerful ones are vulnerable to isolation and reduced physical demand, but they don't necessarily decline at the same rate or respond to the same countermeasures, which means there's no single fix, no one exercise routine, capable of protecting every part of the musculoskeletal system equally across a mission stretching well over a year. For a crew heading to Mars, that means the training program keeping their bodies functional has to be constantly adjusted, monitored, and retargeted for the entire multi-year duration of the trip, not simply switched on once at the start and left running. It's easy to picture bone loss and muscle loss as a single generic category of decline, the body getting weaker in some vague, uniform way. The Mars 500 data says otherwise. Different muscles fail differently, on different timelines, for different reasons, and untangling exactly which parts of the body need which specific intervention, at which point in a years-long mission, remains one of the persistent, unsolved problems standing between where human spaceflight is now and where a Mars mission needs it to be. The third quarter slump. There's one more pattern worth naming from the isolation research, because it tells you exactly when a crew is most at risk, and it isn't when most people would assume. Researchers who study long-duration isolation, drawing on data from HICs, Antarctic winter overstations, and other confined missions, describe something called the third quarter phenomenon, a documented tendency for morale, mood, and team cohesion to bottom out not at the loneliest, most disorienting start of a mission, and not in the final stretch when the end is finally in sight, but somewhere in the third quarter, past the halfway point, when the beginning's novelty has fully worn off and the finish is still too far away to feel real. High Seas data specifically placed the roughest stretch of an 8 to 12-month mission right around the 6-month mark, exactly the third quarter window, with a period of volatility, not steady decline, but real ups and downs, continuing from there until the mission's actual end. Stretch that timeline out to a real Mars mission, running 2.5 to 3 years, and the third quarter isn't a bad week anymore. It's a period that could span the better part of a year, arriving right around the time a crew has left Mars's surface and is somewhere in the long, empty return trip home, the outbound novelty long gone, the actual landing back on Earth still agonizingly far off. It's a strange thing to realize that the most psychologically dangerous stretch of the entire journey might not be the loneliest looking part on paper, the moment of maximum distance from Earth, but a quieter, more drawn-out stretch that simply comes after the human mind has run out of ways to keep treating the unfamiliar as new. What no one has fully lived through. Step back and look at everything this script has actually covered, and one thread runs underneath all of it. Nearly every number, every study, every documented effect described so far comes from missions that top out at around a year, and often far less. Scott Kelly's genetic changes came from 340 days. The bone and muscle data mostly comes from 4 to 6 month ISS rotations. Mars 500 and the longest HIC's mission each ran roughly a year and a half at most. Even the Apollo astronauts, the only 24 humans ever to leave the magnetosphere at all, were only ever gone for a matter of days. A real mission to Mars asks the human body and the human mind to sustain all of these compounding effects: radiation, bone loss, muscle loss, immune suppression, genetic disruption, sleep deprivation, isolation, kidney stress, cardiac atrophy, all of it, simultaneously, for 2 to 3 uninterrupted years, longer than almost any single study on this list, and longer than all of them combined if you tried to stack the worst known effects of each one back to back. Nobody has ever actually done that. Every single fact in this video is either a measurement from a shorter mission, extrapolated forward, or a number produced by a model trying to predict what happens when you finally let all of it run for as long as an actual trip to Mars would require. The extrapolation might hold, it might not. Either way, the first crew that actually makes the trip will be the ones who find out, in real time, with their own bodies, exactly where the models were right and exactly where they weren't. What's left when you look back? There's one more documented reaction to distance, and unlike everything else on this list, it isn't damage at all. It's the exact opposite. It's called the overview effect, a term coined back in 1987 by author Frank White after he sat down and interviewed astronauts about what happened to them psychologically the moment they saw the whole Earth at once, small and complete, hanging in the dark. Apollo 14 astronaut Edgar Mitchell described it this way: "You develop an instant global consciousness, a people orientation, an intense dissatisfaction with the state of the world, and a compulsion to actually do something about it. And from out there on the moon," he said, "international politics start to look almost petty." ISS astronaut Ron Garan described looking down at Earth and seeing something that struck him as a living, breathing organism, beautiful and, at the exact same time, unmistakably fragile, protected from the total hostility of space by nothing more than what he called a paper-thin layer of atmosphere. And in April of 2026, when the Artemis II crew flew 406,771 kilometers from Earth, farther than nearly any human being in history, they described experiencing that same shift in perspective, in almost the exact same words Edgar Mitchell had reached for more than 50 years earlier. That's the strange center sitting at the middle of all of this. The same distance that strips away bone density, wakes up dormant viruses hiding inside your own cells, delays your voice by minutes or hours or entire days, and leaves your mind alone with itself for months at a stretch, also produces the single most profound emotional reaction ever recorded in human beings who've left this planet. The farther you go, the more it costs you, and somehow, at the exact same time, the more it seems to give back. The walls that can't fully protect you. Given everything radiation does to a body, the obvious question is why spacecraft engineers simply don't build thicker walls and solve the problem outright. The honest answer is that they've tried, and the physics involved refuses to fully cooperate. For solar particle events, the bursts of protons thrown out during solar flares, shielding genuinely works. Engineers have found that materials packed with hydrogen atoms are the most effective barrier, and that makes water and a common plastic called polyethylene, the same material found in ordinary water bottles and grocery bags, surprisingly good candidates for protection. NASA has already added blocks of polyethylene to crew sleeping quarters aboard the International Space Station specifically for this purpose, and researchers have proposed storing a spacecraft's water supply strategically around the crew's living space to double as a radiation storm shelter, something the crew would need to duck into during a solar event and then wait out. Galactic cosmic radiation is the harder problem, and it stays hard no matter how the shielding is arranged. These particles move fast enough and hit hard enough that when they strike the metal walls of a spacecraft, they don't simply stop. They shatter atoms inside the material itself, spraying a shower of new, secondary particles into the crew cabin, in some cases actually making the radiation environment worse than it would have been with no wall there at all. The only real way to counter that is by adding still more mass, more shielding, layered on top of shielding, but every additional pound of material has to be launched from Earth's surface first, at enormous cost, which means the amount of protection any given mission can actually afford is set as much by a rocket's launch budget as it is by what a human body can survive. This is the uncomfortable center of the radiation problem for a Mars mission. There is currently no material, no wall thickness, and no shielding strategy that fully solves it. Only ways to reduce it at the margins, trade dollars and mass for a slightly lower risk, and hope the astronauts' own bodies can absorb what's left. The vast loneliness up here. There's a piece of audio, recorded in real time, that captures the emotional weight of distance more directly than any statistic can, and it comes from the same mission that first carried humans farther from Earth than anyone in history. On December 24, 1968, Apollo 8 astronauts Frank Borman, Jim Lovell, and Bill Anders became the first human beings to leave Earth's orbit entirely and travel to another world, circling the Moon, while roughly 500 million people back on Earth watched their live television broadcast, reportedly the largest audience that had ever listened to a single human voice at once. Asked to share his impressions of what he was seeing, Lovell said it plainly, on air, in real time. The vast loneliness up here of the Moon is awe-inspiring, and it makes you realize just what you have back there on Earth. The Earth from here is a grand oasis in the big vastness of space. Borman, describing the same view moments earlier, called the Moon a vast, lonely, forbidding type existence, great expanse of nothing, adding that it certainly wouldn't be a very inviting place to live or work. These weren't scripted lines. They were three men, farther from home than any human being had ever traveled up to that point, trying to put language around something no one had ever actually seen with their own eyes before: the entire Earth, whole and small, hanging alone in the dark. The broadcast ended with all three men taking turns reading from the opening verses of the Book of Genesis, closing with Borman's own words: "Good night, good luck, a Merry Christmas, and God bless all of you on the good Earth." That's the whole shape of this story in one broadcast. The same distance that Lovell called awe-inspiring, Borman called forbidding, in the very same conversation about the very same view. Loneliness and wonder, sitting right next to each other, produced by nothing more than enough distance to finally see the whole thing at once. It's the same reaction the Artemis II crew would describe, in almost identical language, more than 57 years later, on their own record-breaking trip around the far side of the same Moon. Conclusion. So why does space get more horrifying the farther you travel? It isn't because of anything waiting out there in the dark. It's because of what distance itself does to something as fragile as a human body and a human mind. 24 people have ever felt what it's like beyond Earth's shield, and not one of them stayed longer than 12 days. The record for how far any human being had ever traveled from home stood untouched for 56 years before it was finally broken this year by a crew that carried the recorded voice of the man who'd set it by accident, half a century earlier, riding along with them. And somewhere out past the edge of our solar system, a 49-year-old spacecraft carries a golden record of who we once were, transmitting on the power of a single light bulb, growing fainter with every year that passes, carrying a message that will very likely outlive every person who ever heard the words, "Houston, we've had a problem." Distance is the real danger here, not because it's empty, because of exactly what it takes, measurably, physically, and psychologically, from anyone who actually tries to cross it. Every fact in this video came from people who went a little way out into that distance and made it home to tell scientists exactly what it had cost them. The next chapter of that story is still unwritten, and whoever ends up writing it will be doing something no human being has ever actually lived through long enough to fully understand.